What's up, Chem peeps? What in the heck are we gonna do in this vid? We are going to manipulate the equilibrium constant K, breaking it down. 1. We are going to explain what happens to the value of K when the reaction is reversed or multiplied by a factor, and what happens to the value of K when two separate reactions are combined. 2. Express the equilibrium constant in terms of concentrations, Kc, or partial pressures, Kp, for reactions involving gaseous reactants and products, and relate Kc and Kp to one another. Finally, 3. Recognize and interpret the various subscripts that accompany the equilibrium constants. First, recognize that if you reverse the equation, you simply need to invert the equilibrium constant. So let's take a look at a generalized reaction in which all of our reactants and products are aqueous and the coefficients of all our reactants and products are 1. If I write the equilibrium constant expression, it's products over reactants, which in this case would be the concentrations of C and D raised to their stoichiometric coefficients over the concentrations of A and B raised to theirs. Now, if I reverse this equation, recognize that the equilibrium constant is still products over reactant. However, notice now that my products are the concentrations of A and B raised to their stoichiometric coefficients over the concentrations of C and D raised to theirs. Now, I'm going to plug in some artificial numbers here just to give you an idea of how this works. Let's say the concentrations of C and D at equilibrium are 10 molar, and A and B are 2 molar in the forward reaction. The value of our equilibrium constant would be 25. 10 times 10 is 100, divided by 2 times 2 or 4, 25. No calculator. In the reverse direction, equilibrium concentrations of our products are now going to be 2 molar each, and our reactants 10 molar each. So the value of our equilibrium constant here is 4/100ths, 0.04. 2 times 2 is 4, divided by 10 times 10 or 100. 4 over 100, 4/100ths. Genius. So, simply recognize the equilibrium constant of the reverse reaction is equal to 1 over the equilibrium constant of the forward reaction. In this example, 1 over 25, which is 0.04. Math. Second manipulation you want to be aware of, if you multiply the coefficients in the equation by a factor, raise the equilibrium constant to the same factor. Here's my generalized reaction again. Concentration of products over concentrations of reactants, how we define the equilibrium constant. Again, concentrations of C and D to their stoichiometric coefficients over concentrations of A and B to theirs. Notice now I've multiplied that same equation by a factor of 2. My equilibrium constant expression, still products over reactants. Notice this time, however, that the concentrations of the products will be each raised to a factor of 2, the reactants also to a factor of 2. Plug in some numbers to help this make more sense. Again, imagine in the initial equation that the concentrations, the products are each 10 molar, the reactants each 2 molar. Therefore, the value of the equilibrium constant is going to be 25. All we've done is multiply this equation by a factor of 2, so notice how that changes the scripts in my expression for the equilibrium constant. Here, the value of my equilibrium constant is going to be 625. In short, the equilibrium constant of your new reaction, the one that has been multiplied by a factor, is equal to the equilibrium constant raised to that same factor. 25, our original equilibrium constant, squared the factor that we multiplied the equation by, gives us 625, or the value of the new equilibrium constant. Final manipulation. If you add 2 or more individual chemical equations to obtain an overall equation, multiply the corresponding equilibrium constants by each other to obtain the overall equilibrium constant. Boom. Here I have 2 very simple equations. Notice that when I sum them together, I get the overall equation A is in equilibrium with C. For that first reaction, products over reactants, means that I've got concentration of B to the first over A to the first. For that second equation, again, products over reactants, concentration of C to the first over B to the first. And for my overall reaction, the equilibrium constant, products over reactants, concentration of C over the concentration of A. Now, as you think about this, let's plug in some values. Again, these values are simply made up to better understand what's going on here. We're going to do that for both of these initial reactions. So in this first one, the value of my equilibrium constant is going to be 5. The second one is going to be 5 as well. And for the overall equation, the value is going to equal 25. Here, the overall new equilibrium constant for the overall reaction is equal to the product of the individual equilibrium constants. In this case, we're simply multiplying our two individual equilibrium constants to get the equilibrium constant for the overall summed reaction. Okay, so manipulating equilibrium constant, check. Now let's talk about how we can express the equilibrium constant in terms of pressure. Recognize that the equilibrium constant can also be expressed in terms of partial pressure for reactions involving gases. Boom. Generalized reaction. Notice this time, however, that the phases of all my reactants are the gas phase. Now, it's important to note the similarities and the differences in how the equilibrium constant is expressed in terms of partial pressures. Okay, so let's first look at a generalized equation in which we have aqueous reactants and products. Our equilibrium constant, concentration of products over concentrations of reactants. Boom. Now let's look at an equation involving gases. Kp is expressed as the partial pressure of the products over the partial pressure of the reactants. Similar. Notice that here we're expressing the partial pressures of our products over the partial pressures of our reactants. Some important differences though. Ensure not to use brackets when writing an equilibrium constant using partial pressures. Brackets indicate concentration, not pressure. So notice with Kc, we will use brackets, but with Kp, we're simply going to use a large letter P to indicate partial pressure, and then the subscript is the formula for that reactant or product, raised to, again, the stoichiometric coefficients in the balanced chemical equation. That part stays the same. Lastly for this vid, recognize that sometimes you're going to see subscripts accompanying your equilibrium constant simply to convey additional information. However, in all cases, it's simply defined as the ratio of concentrations of products over reactants. For example, you've got your acid dissociation constant, or Ka. Again, concentration of products over concentrations of reactants, and in your generalized acid dissociation expression, but also think of our good friend Kw, or the ionization constant of water. Again, concentration of products over concentrations of reactants. Although recognize that for Kw, the only aqueous species, and therefore the only ones that will show up in our K expression, are going to be our products. Another really common one, Ksp, or our solubility product constant, for those only slightly soluble salts, again expressed similarly, concentration of products over concentrations of reactants. Although, again, notice an expression like this, we're only going to see our aqueous species expressed. In this case, it will be the aqueous products, raised to their stoichiometric coefficients. Now, that's just a sampling of some of the K expressions that you're going to use in the class, but simply recognize that the subscript provides additional helpful information about the type of reaction that's being performed. It does not change the definition of K. Products over reactants. All right, and that does it for this vid. Have a fantastic day.